Hi guys, so everyone here welcome, and everyone online welcome as well. Welcome to the UQCS and UQMARS collaborated path planning workshop. So path planning, there's a lot of applications of it in the real world. I mean, if you use Google Maps itself, that's path planning. I'm sure if you use like an old-fashioned map, you'd kind of do path planning in your head, even though you wouldn't know. And since we are the Mechatronics and Robotics Society, the place we are most interested in is how it's used in robotics. So obviously we can't cover like actual like implementations of it in 2 hours, but we will go through some basic theories and stuff that I will go over later. We also like to thank our sponsors that I've shown on screen. Without them, we wouldn't be able to do this. I have the pizza you guys are going to have later. Sorry to the people online. Yeah, so here we have some examples of path planning. So the top left is something called SLAM, which is simultaneous localization and mapping. The robot might not be doing planning, but it's following the path, that blue path that you see, and mapping the obstacles around it that it detects. The one on the bottom, that's probably a simulation. So the walls and stuff would be characterized as what we call obstacles, and you'd use the algorithms to find the shortest path to get to that green point over there. Bottom right, I'm pretty sure some of you might have heard of it. It's called micromouse. So the idea with that is you get 2 runs. The first run is kind of a mapping run. So you go through it and you get the map of the maze because it's going to change each round. And after that, you go back to the start point, you'd apply your algorithm. So whether that be complex or just one of the ones that we're covering later. And then, yeah, as you can see here, this is the fast run that they're doing. Top right, it's not really path planning. I guess it's just mapping the environment. Since we already have the map, it's just trying to see if the robot can get the map. So the navigation system of a robot at its like very high level, so at its lowest level, we just have the perception system. That could be like your sensors, your ultrasonic, your LiDAR, stuff like that. And that gets fed into a localization system. So that one, like what I was talking before, the simultaneous localization and mapping, stuff like that, it gets fed into there. And then from there, we need to define a start and end point, right? So the position that we want to go to from the current position. And so that's where the path planning comes in. So your task and objective is, let's say I want to go to that door over there. My current position is where I am, and that gets fed into path planning. After that, we do something called motion control. So if I know how to get from here to the door, I haven't defined anything about how am I going to get it. Am I going to go around the table? Am I going to go at what speed? How fast can I run? Stuff like that. So today, as I probably have mentioned multiple times, we will be focusing on the path planning aspect of this. So a theoretical definition, path planning is a process used to construct a path from A to B, given a partial or dynamic map. So a dynamic map is, let's say you're walking to a room for the first time, and I know where the door is, but I don't know what's past the door. So this path planning algorithm will calculate the optimal decision that you take once you go in the door and see what's in the door. So a few popular categories. We have grid-based search, which we'll be doing today, so I'll cover that later. We have sampling-based search, which is kind of like you could randomly sample the points until you get the best path. And then you have ML-based search, which is like using reinforcement learning and stuff like that to get a more optimal path. So before I mentioned path planning and motion control, there's kind of a sort of step in the middle of it called motion planning. So that is using the waypoint. So let's say I'm going from here to the door. It's a set of points that, or it defines like what I need to avoid, like collision avoidance, whether there's dynamic collisions, and like your joint limits, your speed, stuff like that. So, could I get a raise of hands? How many of you think this is path planning? How do you guys reckon? So path planning is, you're trying to find the waypoints between a few points, and motion planning is actually determining how you're going to execute that path. So could I get a show of hands? How many of you guys think it's path planning? We have one there, yeah. So this is path planning. This next one here, since we already have the, it's kind of both, right? Because the green defines the waypoints of how we're going to get to the path, and then the robot has the 4 links, which is doing motion planning to execute. Next, we have this one. This is kind of like both of them together again. So the red points that you see are the waypoints. So let's say I'm going from here to the door to the outside door. That'll be the red points. And then the green trajectory, is what we call it, is how I'm going to execute that point. So before we start, it would be good if you guys could clone the UQMARS workshop resources directory. That's what we'll be using today. Within that, there is I might go through it here. Within that, we have within that, you have to download or clone another repository, which I'll show you guys how to do quickly. Yep, so go to the UQMARS GitHub, workshop resources, and then path planning. And from there, you're going to clone or download a copy of this repository here. So if you're trying to clone it, you guys should know what you're doing. Just copy this, and if you're trying to download it, just use this. So if you don't have Git, you would probably download it and open it in an IDE such as VS Code. So I'll give you guys maybe 2 minutes to do that.
Just let us know if you need help cloning that as well.
Yeah.
It's me taking it from here, right? I'm too big for this. Should I? I'll just do it.
I believe the link to the GitHub is also in Discord and the stream.
It'll be weird if I just put it in from graph basics.
No, I'll do basics.
Oh, you're doing,
Yeah, I'll do everything, and then you do 2 examples. So we can review 2 examples. All right, so you still have time. I'll just continue for now. So the agenda today, we're going to cover some basics of graph and node theory, and then we're going to cover breadth first search, which is BFS, and depth first search, which is DFS. They're 2 of probably the most basic algorithms that most people would know of. After that, you have the concept of cost functions. So breadth first search and depth first search, they're both undirected. So they search regardless. Let's say I'm trying to go again to the door. They literally search every direction, but they don't know where the door is. So they're searching in a systematic way until they get to the door, but they don't actually know how close they are to the door or how much effort I have to put in to get to the door. So there are a few algorithms that consider that, which are called informed search algorithms. And we have Djikstra, UCS, which is uniform cost search, and A star. Yeah, these are just some names, don't worry. Trying to get them right now.
Has anyone heard of these algorithms before this tutorial?
Yeah, sounds good. All right, let's carry on. So graph basics. I think some of this is quite intuitive. So usually we represent the environment as a map. So this is grid-based search. what we're doing today, as I mentioned before. So I'll go back up. Yep, so this is a grid-based search. So there's two ways of representing it. We have a graph and a tree, and this is the graph. So you have two kind of common set of terms, which is edges and a set of vertices. So the edges are the paths that connect the nodes. So the vertices, let's say in my top right, I have A, B, C, D, E, F, G, H. Those are my vertices, and the edges are the path that connect these vertices. The bottom right, you have, so Brisbane and Sydney would be my nodes, and then the line connecting them would be the edges. And the 749 km is a cost. So if I go from Brisbane to Sydney, it costs me 749 kilometers. That's how much, like, it's a distance. After this is just another term. So graphs can be directed or undirected. So undirected graphs are graphs where the edges don't have arrows on them pretty much. So you can go, I can go there and come back. So let's say I can go to the door and come back. Whereas directed graphs, depending on what sign they have, you might be only able to go one way. So we have a graph of the UQ kind of thing that we copied from somewhere, but yeah, so there's, as you can see, most of it's directed, except from AB to building 50, you have a undirected portion, but since the graph already has directed edges, it's still directed. So basic search algorithm, so depth first search, right? So depth first search, pretty much, let's say you're in a maze, right? And while I'm walking through the maze, I'm always going to turn right until I get to a dead end. And then I'm going to go all the way back to the last time I saw two intersections. So if I go right, I keep going right, and then there's this point where I can go right and left. I'm going to keep going right until I get to a dead end, and then I'm going to backtrack back to the point where I could go left and right and go left. So for those that uses queues, this is a last in, first out queue. So from the analogy I was using before, at the intersection I could go left or right. I keep going right until the dead end. And on my queue, the last thing that I put on would be the left. So I'd go back to the left and continue my left path. So we have an example where we might do this after. So the next one is breadth first search. So this one explores the graph one layer at a time. So if I go back to my example before, say I'm at the start, I move one step and I could go right or left. I'm going to go right and left one step, and then after I'm going to go right again. So you don't go more than one step until the dead end, you just stop at the first step once you've explored it. So I'm going to hand over to Ash now. We're going to do an example with this. Breadth first search first.
Hello everyone. So I'm going to go through BFS first. So this is just a map of the UQ. Yeah, we've got UQ Lakes there, Building 78, and Advanced Engineering building there. I've never heard of Wordsmith before, but yeah. So our goal state is Building 7, and we had to traverse through these paths to reach 7. So for BFS, as Shenka said before, I like to think of it as like you're going through each layer of an onion, because onions have layers. And then, so yeah, I'll go through that now, but it's really easy. So you start off in a left or right direction. This is implementation based, so it really depends on whatever you want to explore first. So if I start off on the right hand side first, so I'd explore these two parts, and we're trying to find building 7 here. So I'd explore these two, and then that's the first like layer done, and then you move on to the second layer. So building 78, explore here, and then we realize building 7's not there. So then we explore this layer here. So this area I highlighted is the second layer, and we still haven't found building 7. So then we keep exploring from the second layer, and there we go, we have building 7 there. It's pretty easy. But yeah, is there any questions on buildings on BFS? Yeah, it's pretty easy. And it depends on the direction that you search as well. So if I searched from the left-hand side first, so explore these two.
That's
Oh, yeah.
right. Yeah.
So then these would explore, this will be the second layer you explore, and then you'd actually find building 7 first here. So then the path that you actually found was a new path in this direction. So it's dependent on the direction that you search, this algorithm, and it's just to get you a path. Like there's nothing about optimality in this. I think it's an uninformed search. I don't know if Shenko mentioned that, but
Yeah, DFS.
yeah. So then we got DFS, which is the maze analogy that Shenko was going through. It's just going straight into a maze and then turning once you hit a wall. So this one's really easy. Sorry. So yeah, you just continue in a straight line. I'll do the right hand side first because it's a bit more nicer. So you just continue down through here. So that's not, you hit a wall here. So then you go back to your last node with the turn, and then you keep going down, and then you find building 7. Yeah, and like BFS, it depends on the direction that you search. So if I went on the left-hand side, it'll just keep going down and eventually find building 7. So these are the 2 easy ones. Is there any questions on this? Have I cooked the explanation? Nice. Yeah, so now we have some code for this that Shenka's going to go through.
All right, so firstly we're going to implement breadth first search, and it's not actually in the repo that you guys have, so I'm going to write it from scratch right now. All right, so you could use queues here, but I'm going to just use lists just to keep it simple. So first thing we're going to do is we're going to define our graph, right? So look at the back. Yep, so I'll get back up my tablet. So let's define a graph, and I'm gonna, one sec. Yep, so I'm gonna define this graph here. So from A is connected to B, I mean, it's pretty simple. So firstly, we have to come up with a list of adjacent nodes, right? So when we're implementing this, first thing we do is come up with a list of adjacent nodes for this implementation. So if I'm at node A, if we go in alphabetical order, and we're making straights, and my writing's bad. Yeah, so straights are better than diagonals, all right? I don't know how, yeah, it's not very readable, but yeah, let's go. So from node A, we're going to B first, and then we're going to C, and then we're going to D last. From node B, we're going to A first, and then we're going to D, and then we're going to E. Is that right? Yep. Yep. And then from C, again, alphabetical order, we're going to A and then to D. D, we're going from B to C to A, because A is diagonal again, remember that. And then for node E, we can only go to B or D. All right, so I'll put this at the side. Is that readable for you guys? Does that make it bigger? Nice. All right. So first thing, we're going to define a dictionary. I'm going to call it graph. You guys can follow along if you guys wanted to. Let me know if I'm going too fast. So we're going to define A first, node A. And pretty much just going to copy what I have there. So we're going to B, and then C, and then D, and you want to put this in a list. Alright, I'm just going to copy this 5 times. Alright, next thing we have is B, and we're going to ADE. We have C, we're going to A and D. And then from node D, we're going to B to C to A. This is diagonal. And then last one, we're just going from B to D.
Is BCA. Missed E for B.
Oh, okay. Yeah, so Ash just pointed out I'm missing an E here, because we could go this way. That'll be the last one. Alright, so now that we've got our graph done, we can start doing our DFS function. DFS, sorry. And into this function, we want a graph. We want to pass our graph, and then we also want to pass the starting node that we are at right now. So I'm just going to start at A. Wait, what am I doing? All right. So first thing we're going to use is a set. I'm not sure how familiar you guys are with Python, but set's pretty much you can think of it as a unique list. So if you append, let's say I already have A in there. If I append A, it's not going to add anything. But if I append B, it's going to append B. Yeah. Same mathematical connotation with the set. B-I-S-I-T-E-D. Am I spelling this wrong? All right. Next thing, I want to keep track of where I've traversed to. So this is my BFS. Call it. Actually, we'll leave that out for now. We need a queue. So this queue is going to tell us how many paths we have left to explore. So if I go back to Ash's example of DFS, I went here. He went here and then here. So let's take this level as done. And then I went here to here. So these two will be on my queue, right? But after I do this one, I take this off the queue, and what's left is only this one here. So we have the queue here. So this is, I'm just using a list for now. And so first thing, we visited node A. Let's append node A to this. And then we've also visited node A. Add. Next thing is, so we already have something on the queue. So we have node A on the queue, and in terms of this analogy, the first thing I'll have on the queue is UQ lakes. So while queue, we're going to pick something off the queue. So queue.pop, list.pop just returns you the last element on the list, I believe. That's right. Yeah.
Yep. Most recently.
No, actually, I think we're going to pop first. It should be the first element, BFS.
Yep.
Yep. So we pop the first element, and then we're going to add this to my traversal list. So this is what I was talking about before. Remember how Ash was going through, the final path that we got was through A, B, building 51, and building 7. So this list is going to store this path, and we get it. So we'll call it BFS path. And we're going to append this to that path. So BFS paths. Append current node. Next thing is we're going to make use of our graph here. So if I'm at A, I want to explore B, C, and D, right? So I'm going to use a for loop here. So for A nodes in Graph. And then now we're going to check if it's building 7 or not. If it's not building 7, we're just going to keep going. If it's building 7, we want to exit. So we have if. I'm going to get rid of this one for now. Oh, sorry, that was for later. So this is just checking. I don't want to explore the same node twice. So before, let's say you go to AEB before, and then you have another path that leads you to AEB. I don't want to explore it again. I just want to go to the next available option. So if it's not in visited, we're going to add it to visited. And we're also going to add it to our queue, because we haven't explored this path yet. Alright, so at the end of this, right now we're not going for the target node, we're just trying to traverse through the whole graph. So we're trying to go to points A, B, C, D, which ultimately one of them will lead you to E. But we're just trying to go through all of the paths for now. And after this, we'll add a goal. So after we added this while loop, we're just going to return this BFS traversal. Alright, we're going to store this. Oops. I'm going to start at node A, as I said before. And then I'm just going to print it. So if I go ahead, I might wait for a while. Actually, I can just put it aside. So if I go ahead and run this, from path A to get to path, it's just going to explore everything. So it's going to A, B, C, D, and E. Whereas, let's say I started at C. We're going to go C, A, D, B, E. So if I bring it back to before. Why does this keep disconnecting? Sorry, one sec, guys. Alright, so path that we got here, CA, let me just write it down. C, A, D, B, E. If we look at the implementation here, we start at C. What's my next node? It's going to be A. We go to A. Right, obviously we'll export D next. And then once I'm at D, the next one is B. So I go to B. And let me just write this. So C to A. C to A, and then I go A to D, sorry, C to D. And then from D, the next one is B, so I'm going to B. And then from D, I still have E left over, so I'm going to E. Right, so that's BFS. I don't know if I went through it too fast. Anyone have any questions? Yes.
Given that we visited A before D, shouldn't we lead off from A for our second layer?
Given we visited A before D.
When it's added to the queue, will be added
Oh, yeah,
when
yeah,
we
right.
take the first element.
Yep. You mean this one here, right? Like that.
We should go A, B, and then
Yeah, D.
D, E.
Yep.
Then D, E.
Oh, yeah. A, B. Wait, is it? Yeah,
A,
it
B,
is.
and no B, D. Because our queue is A.
We should go from B to E.
No, because D is on the queue before B is.
No, so we start at C, right? We go to A,
Mhm.
right? And then we go to D, right? So
Yep.
we go here first, second, right?
Yep.
And then now we just export A first.
Yep.
We go to the first one. Can't go to C. So we go to D. No.
No.
No, we've already been to D. Yep. So we're still at B. So now we're at B.
B should be third on the queue by that point. Because we already have D.
Is that right? Let's see. We're going to A. It should be right. So you're saying it's C, A, B, D.
No, like the output's fine, but like.
Oh, the way I drew it?
Yeah, it
Yeah.
should go from D to E, not B to E. I could be mistaken.
No, that's probably right. So you're saying we're going to C to A first, C to D, and then.
Yep, and then A to B, because A is the first on the queue at that point. It gets
Yes,
removed.
correct, which is this one.
And D is next on the queue.
Ah, from C, yeah.
Yep. So we have to go from D to E.
My bad, yes, thank you. I get what you mean. Let me just put that on the board. Yep, so again, if I do this again, let's use a different color. So from C, we'll first go to A, right? This is number 1. And C, we still have D left over. I mean, yep, so we're going to D. It's number 2. And then we go back to A. We've already visited C, we've already visited D, so we're going to B. And they're right now on the queue, the next will be D. The next is going to be D, and from D, we've already visited B, visited C, visited A, next one will be E, so we go to E. Thank you for pointing that out. Right, so this is the BFS implementation. Now we are going to go to the repo that you guys cloned, and we have the run DFS file. I might rewrite this one. Yep. So we'll go. Right. So let me just get that up as reference. Alright, so we're going to import the same things that they have. Oh, we don't need functions actually. You can run, so if I run the base DFS file, one thing, so what you guys would have had, it won't run. So the stock code that you guys have won't run, so you guys need to go into functions.py, and this hex code that you see here, you just need to delete it and change it to something random, and it just has to be even number of numbers. So you get 0x, any number from 0 to 9, and any letter from A to F. Right. Yep. So we'll come around and help you guys with that later. I'll just come around. Can you guys not open it? Just to fix up the functions file first, and then we'll carry on.
It's just the hex.
We're changing this is so the person that wrote this code, the way they generate the map would be to use the hex code to define where my obstacles are. So for example, if I leave it now and I run the A-star algorithm, right, so that hex code defines where my black dots are. Those are the obstacles. So the way that he did it for DFS, which is what we're going to implement, there was two obstacles next to the start node, so we couldn't actually get out of the start node and it would crash. And we're just going to functions.py, and we're changing this hex code. There is an example though. If you guys can't think of a random hex code, if you go into path planning and scroll down, there is an example here.
folder is it? Path plan?
Yeah, put it in path plan. Okay, let me look at this sheet. Just go to history. Wait, no, it's not that. Wait, come back. You just updated the read.
I'll update on.
It says here.
Okay, so after you guys change that, you should be able to. Yeah, so after you guys change that, you should be able to run the function. Run dfs.py. We're not going to write it again because it's 547, but I will go through it. And so this is, yeah, as you can see, it's going to do a bunch of stuff, but the path that it finds is not the optimal path because DFS will just return you the first path that it finds. So the purple stuff you see there would have been like one of the nodes that it took. Let's say if I'm going right and the path is on the left, it would have taken right and it went through on a tangent to the purple path, and the orange path is the most optimal. The first one that it found. And if I run this again, it's going to give me a different.
Except if there's no.
It's going to give me different ones each time because he's using a random DFS. So if I got rid of this random shuffle right here, so that's on line 39, you'll see that because we're exploring the path using an array, it's just going to go through each row at each time. So I'll run that now. It'd be easier if I get rid of this. Yep, so if I reduce the number of obstacles and then we look at how DFS does its stuff, it's literally going to go through each row at each time. And that's because we're traversing through the array without any randomness. Yeah, and then not surprisingly, it's going to return no path, apparently. I'm not sure why that happened, actually.
Is it to do with the fact it doesn't want to loop back?
It should loop back as long as it doesn't find anything.
Yeah. Should is strong.
Yeah,
Yeah.
it's already visited. He's right.
Yeah, he's right.
It should loop back though.
But it's already visited, like it's off the heap. Like,
Yeah, like because it's visited that path already, it can't go back
Yeah,
on just because
just that.
we've told it to not keep looping back.
All right. So these two are uninformed search. As you can see, they won't return you DFS won't return you the most optimal path. It's just going to return you the first path that it finds. And BFS, which was the first example that we did, will return you the path with the least edges. So I'll go back to the PowerPoint slides here. So breadth-first search, even though it traverses the whole graph, right? The number of vertices that you have, so let's say from Brisbane to Sydney, I could easily have done another one going from Brisbane to like Melbourne or something. And if I didn't have that 749 kilometers there, you wouldn't know how much more effort it takes to go to Sydney than go to Melbourne, right? But in path planning, we want to define kind of like a cost for the steps that we're going to take. So that's when informed search algorithms come in. So what we've done so far is BFS and DFS with the uninformed. They don't take into account how much something has cost me to get to the point I'm at right now. So the goal state that you find probably won't be the one with real cost. A real life example would be, let's say in the node graph I had before, I had, let's say I'm starting from here, which is AB, I'm going to UQ Lakes. I could have done, I'm going from UQ Lakes, AB to like the car park at the back and then to UQ Lakes. Or I could have done, I'm going from AB to like the coffee shop down there to UQ Lakes. And we know the path from AB to coffee shop to UQ Lakes is obviously faster. Maybe not now because of the construction, but if we were using BFS and DFS, it wouldn't know which one's better. So this is why we have informed search. I'll hand over to Ash now. We're going to put some values of cost on the graphs that we were doing before. You can see how that plays out.
probably will not. It's pretty easy there. We can get that set up on the side. I mean, like going through this because I was just going to count. Yeah. So just to reiterate from what Shankar said, in reality, each path you take has a cost associated with it. So BFS will give you some path to the goal, but relative to the cost, it might not be the most efficient cost. So it might not be the most efficient path. So finding the goal state is not enough. You want the path with the lowest cost. So here's an example if we take from the paths that we got from the BFS and DFS. BFS is the green path that we found, and that's a total cost of 150. And the DFS path is a total cost of 120. So to calculate the costs, you just add the paths together. So the green is just 70 plus 20 plus 60, and the yellow is 50 plus 30 plus 40. So we need to find out a way to consistently find the optimal path.
Which one's the optimal path?
And the optimal path is the path with the least cost.
On the graph.
On the graph. I'm not going to show you it now because it's going to be a spoiler. I want us to figure it out together. But I'm not sure if we should continue because I'll give it 10 minutes. So, introducing the Dijkstra's algorithm. Has anyone heard of the Dijkstra's algorithm before? It should be a really, yeah. So, it's widely used in real-world applications, according to Google, such as GPS navigation systems, network routing protocols, and airline travel planning, apparently. It was invented by a guy called Djikstra in 1956. So the idea is to compute the shortest path from a starting node to all the other nodes. Here is a little pseudocode that I copied last minute. Does anyone want me to go through this? Oh, no. Yeah. I was going to go through an example on the tablet, but I'm not sure if we should have pizza now, because this is about like a 10-minute example. So I think we should just reset and have a pizza. What do you guys reckon? Is that a fair call? All right, yeah. Pizza.
Yes.
Welcome back live to 7 News. Today we're going to be sorry, we're just waiting for some people to come in, for the guys on the stream. So, hello everyone. Can I get your attention? Sorry. So, we just introduced the Dijkstra's algorithm, which accounts for the costs of the paths, as opposed to the BFS-DFS, which is just a straightforward algorithm. So I'm going to go through an example of Dijkstra's algorithm now, based on the map that we've got. So one thing to note is that we've updated the map with costs to each node. So this cost will usually relate to like a distance between the nodes. So a larger distance means it's further away. So we want the path that's smallest, so closest. So please correct me for those guys that already know Dijkstra if I cook something. So we start off at our start node, which is the UQ Lakes. So when we start, we assign that node a total cost. Sorry, I'll go through this list here. So on the right here, we have our list of nodes and their cost on the right here, as well as if they're explored or not. So we start off exploring UQ Lakes, which is our start node. Draw it in here. So we explore our nodes from UQ Lakes, and we find that AEB has a cost of 50, so it's 50 meters away or something, and building 78 has a cost of 70. So that's our first search. After each search, you want to explore the next node that has the least cost. Yeah. So in this case, we want to explore AEB because that's got 50 as opposed to 70. So then we update our little table on the right here. So then we say 50 for AEB, and that is the new shortest path to AEB. So so then we keep track of the shortest paths as we go. So now we explore from AEB. So we find building 51 at a cost of, so with these costs, you want to add the total cost. So it'll be 50 plus 30. So we have a total cost of 80 for building 51. And then we explore down to building 50, and we find a total cost of 65. And then we find building 78, which has a total cost of 60. Am I making sense so far? So then you do the same thing, but one thing to note is that we have two 78s here. So if this happens, you just pick the node with the least cost and just ignore the other one because it's already not optimal. So we ignore this guy here. So then we explore the path with the least cost, which is building 78. Yes? Yes. So then that is our new path. And then we add it here to our table of contents. Sorry, these are explored. So now that 78 is the most optimal, we explore from 78. So then we explore here, and we find building 42 at a cost of 50 plus 10 plus 20 is 80. And then we got Wordsmith at a total of 50 plus 10 plus 30. So that is 90. So yeah, and then we just repeat. So the next lowest cost is building 50. So we explore to 50, yeah? And then we add that to our table. Building 50 is 65. So this table represents all the optimal paths, this table up here, and the associated costs. So we explore from 50. We find building 7, which is the place where we want to go, at a total cost of 50 plus 15 plus 40. It's a tough one. 105. Nice. And then we have, yeah, so that's the only one there because this is a going in that direction. So then we repeat the same thing. We explore the path, the node with the least cost. So you see we have two 80s here. So this is where it's dependent on the user's implementation, whether or not which node to explore. I'm just going to choose the building 51, but this is up to the coder, I guess. So explore 51, which is this node here. We add it to our table. So that's 50 plus 30, that's 80. And then we explore from building 51, and we find building 7 for a total cost of 50 plus 30 plus 40. It's another tough one. 120. Nice. So you can see we already have a building 7, and it's less than 170, so we just ignore that node. So then, yeah, same thing. We get the next node, which is building 42. Add that to our list. Say it's explored. That is this path here. So we explore from there, and we find building 7 again. And this time the cost is 50 plus 10 plus 20 plus 60. 140. Yes. But that's already larger than 108, so you don't include that guy. So then our last one is, we have 2 more. We have west, which is 9, wordsmith. So this is the optimal path here. It's added to our list, 90. And then we got building 7, finally, which is 108. So we include that right there. So that's how you find, that's Dijkstra's algorithm. And the good thing about this is it finds the, these costs here are all the shortest costs to those paths. And the good thing about this is after you store the ones you explore, so let's say we've just found building 7, you can backtrack along the optimal path, because the optimal path would be a sum of optimal paths, if that makes sense. So you just backtrack here, because you know that's optimal, and you know this path's optimal, and you know this path's optimal. So then this entire path will be your optimal path. And that's how you keep track of it in the code as well. You want to save where it came from. So then all you have to do is just backtrack to your start, and you have the optimal path there. I don't think I cooked it. Was there any questions or any things you want me to clear up with this guy? Okay, nice. So that's the Dijkstra's algorithm. So when Djikstra was alive, he had some famous quotes. And these quotes relate to his algorithm. So the source is Wikipedia, so keep that in mind. So the first quote is, "Be like water, my friend. Water can flow, or it can crash." So the lesson taken from this is that once a node has been explored, it becomes the optimal path. Think about that. And leave no stone unturned. So the algorithm does not stop until all the nodes have been explored. That's a pretty self-explanatory one. And then the last quote was, "Those who do not learn history are doomed to repeat it." Make sure, so yeah, the lesson from that is make sure you keep track of how you get to a node so you can backtrack and find the previous node. So remember, these sources from Wikipedia, and that's a nice little diagram there on Dijkstra's. So yeah, so the pros of this is it finds the shortest path to all the other nodes, which is good. It's guaranteed to find an optimal solution based on the costs, as opposed to DFS, which is just any path. And it's pretty simple and easy to implement. You can see I was repeating the same steps, which was just whatever's the shortest node, expand it. And the cons are, it's inefficient when you're dealing with really dense graphs. So if you have a lot of turns, you'll use a lot of memory. And it can't handle negative edge weights.
I have a question.
Oh, okay, yeah.
So why can't it handle negative?
I forgot the answer.
Yeah, so in Dijkstra's, we always assume that we're finding the optimal path for each node we go to, right? So pretend I had node A, B, and C, right? And in the case if we had optimal weights, let's say the cost to go from A to B was, one sec. So the cost to go from A to B was 7, and the cost to go from B to C, we'll say it's -10. And the cost from A to C, we'll take it as like 5. So when we're doing Djikstra, right, we're going to go from A to C, right? Because that's if we're at A, if we go to B, it's 7. If we go to C, it's 5. So we're going to say A to C is the optimal path. But then if we have a negative weight, if we go A to B to C, we actually have 7 minus 10, which equals negative 3. So that assumption where we take that the optimal path is always found when we go to the next node is not valid. Another way. Yeah, so we're assuming that when we get to a node, it's already the minimal parts of that node. Whereas in this case, when we get to the node, we don't know if there's any other better path than a node. So it pretty much destroys the concept of that in Djikstra.
Thank you, Professor Schenker. So yeah, it can't handle negative edge weights, and it uses a lot of memory to search the optimal paths of all nodes. Yeah. So introducing the next algorithm, which is the uniform cost search algorithm. Instead of finding the shortest path to all the nodes, why don't we just find the shortest path to a specific node? It's the exact same process as Djikstra, but as soon as you find the node you're looking for, you just stop the algorithm because you don't care about the other nodes. Yeah, flashback, be like water, my friend. So once it's been explored, so once you found it, it becomes the optimal path. So I was going to go through another example, but it's the exact same example, but you would stop at once you find it. Do I? Yeah, now you guys are good.
Yeah, so that's...
So UCS also has some famous quotes, and it's the exact same as Djikstra because it's the exact same algorithm. Yeah. So UCS in a nutshell, it's the shortest path to a specific node rather than all the nodes. That's the plus side of that. It's faster than Djikstra because it stops at that node, but keep in mind they're used for like different implementations. Sometimes you want the shortest paths to all the nodes, and sometimes you just want one node. And cons all the negatives from Djikstra because it's the exact same algorithm. So we can find the shortest path, and it's pretty easy. But how quickly can we find it? Just like that. In reality, as the graph becomes more complex, UCS becomes slower because it expands unnecessary paths. A path might look optimal in terms of cost, but it could have no correlation to the goal node we want to reach. So imagine your goal is in the north direction, but you find that your nodes in the south direction are cheaper. The UCS algorithm would search that way before it even considers the nodes that way. So like, yeah. So we need some way of telling which node or which way to go to improve the speed of the algorithm. So introducing the A-star algorithm. So the A-star algorithm uses a heuristic function to estimate the distance from the current node to the goal node. It can be thought of some sort of guess or a guide towards the remaining node, just to keep us towards the right track. So it combines the cost, which is the values in the values you saw before, like these costs here, and then it has some other heuristic value. Yeah, it just sums those, but it's the exact same algorithm. Yeah, okay, I'll do this algorithm, sure. So for A star, it's very similar, if not the same. It's just that these white values, those are the heuristic values, which should make us search less and search more towards the goal node. So if we start it again, start at UQ Lakes. Remember, remind me if I cook it, please. But we search from UQ Lakes, and we find AEB. Sorry, so UQ Lakes has a total cost of 0, is the start, and it is explored. So we find AEB at a total cost of 60 this time, not 50. I'll explain more how we generate a heuristic function later, but we'll just go through the algorithm now. So then you have AEB at 60, and you also have building 78 at 50 plus 70. Tough one. It's a 120. So you got building 78, 120. So then we explore A, B, and that becomes the optimal path. So that's 60 explored. We explore here, here, and here. So we find building 51 at a total cost of 60 plus 30 plus 29, 119. And then we have building 50, which is 60 plus 20, which is 80. Building 50 is 80. And we have building 78 over here, which is 60 plus 15, which is 75. So then we do the same thing. What's the lowest part? What's the lowest cost path? Which is building 78, and we add that to our list. Add a 75, and we expand from that node, and we get these two. So we find wordsmith at 60 plus 15 plus 60, 135, I think. And then we find building 42 over here. That is 60 plus 15 plus 40, 115. So then we do the same thing. We find building 50 is the lowest, add that to our list, and explore from building 50. And we find building 7 valued at 60 plus 20 plus 45. 130. 130? Yeah. 130. So then you explore building 42 because that's the lowest, shortest path. And we add that to our list. And then we find another value of building G, which is 115 plus 70. So that's like 185, but it's already higher than what we already have here, so we just ignore it. And then we explore the next shortest path, which is 51, which is here. And then 51 gives us another BG, which is another really big number, but it's higher than the one we already have, so we don't care. And then we go building 78. Where is that? That's here. And we find wordsmith. Oh, sorry, that becomes here. Yeah. But as you can see, I've cooked it. But but eventually we find that building G, we find this guy here. Eventually. And it should result to lower amount of searches because of the heuristic. Any questions? Thank you. So that's the A-star algorithm. So the hard part about this is the heuristic. So how can we create a heuristic? So this is usually based on prior knowledge of the system. So some common examples would just be the Manhattan distance or the Euclidean distance between the current node and the goal node. So this will just be like, if it's on the right, then it'll just be, if it's on the left. Yeah, it's just, yeah. So it's just like saying that's right. It's more towards that direction. Yeah, because it's closer. I cooked that one too. But yeah, it's just some way of guiding it towards the node. This is usually a hard part because it might be closer this way, but there might be a wall in front of the way. So that path might not actually lead towards the path. So maybe you need to take the long way around, and that's actually the shortest path. So yeah, the heuristic is the hard part of A-star, and it must be admissible. So you should never overestimate the actual cost of the path, which makes sense because you don't want to, it's basically your word against the actual cost. You don't want to give more value to your guess because it's just a guess. So he's got some famous quotes, A-star algorithm. If you know the enemy and know yourself, you need not fear the search of 100. You need not fear the result of 100 searches. That's his first quote. And the second quote is, those that spend the most effort in search of shortcuts are often the most disappointed and least successful. So yeah, if the heuristic is incorrect, it can actually lead to more searches, which is the analogy I gave with the wall. So maybe you need to actually go take the long way.
A-star was the best guy.
Yeah, there's multiple stars there too. I'm sure there's a whole generation of stars. but this is the star. But it's pros and cons. Yeah, it's the same. Finds the shortest path to a specific node to another node. It can be faster than the UCS if the heuristic is correct. And is, yeah, all the other pros from UCS, all the good stuff.
What do you mean by correct heuristic?
So, sorry, a nice little quote, little thing there. So what's the difference between a correct heuristic and an incorrect heuristic? So an incorrect heuristic would be saying like it's going in the wrong direction, right?
Yeah, what overestimates?
Yeah. So an incorrect heuristic would be example of when you overestimate the cost, that's what I said before, or if it's just completely incorrect, like the goal's over there and your heuristic function's saying go that way. Like that's just your correct and incorrect heuristics. That was good. Oh, it's done. But our photography specialist, CV specialist, Miguel, has an example of A-star he wants to show.
Yeah, it should be on GitHub as well.
I'm going to let him do that.
You got it on GitHub or should I just put it here?
Yeah.
pull it?
Do you pull?
Otherwise I can show it here.
Because they had to stream it.
I made some modifications. Let's see.
This is all you.
I don't have the picture.
You can pull.
Where's the save?
Save it. Go back.
Where is it? I don't know where it is.
It's not saved yet. You didn't pull.
Go clone it. I don't know what the clone is.
It's here.
We already have it. Okay.
This guy.
I didn't know you had it set up. How should I? How do I know it's your clipboard?
Don't worry. You're gonna change one.
I don't need to pull it.
Yeah, it should be the latest, right?
Where is it?
You gotta go back to it.
Do you want to close it off? Which one is it? Oh, it didn't clone. What the heck? The image didn't copy. Maze generator. It wasn't there. Cool. Okay, wait, this is how we mic'd up. Oh, we mic'd up good. Cool. So let's get started.
Just started, guys.
Yeah, we're starting. Okay, could you guys, for this thing here, you should be able to locate the resources on the GitHub still. It should be under path planning and then maze.py. So this is an application of the maze, sort of similar to what we saw before, but in this we're going to be testing Dijkstra's algorithm and as well as A-star, right? So for this, what you're going to need is an image of a maze, right? And essentially, it'll solve the maze just like this. Let me just create this. Yeah. So I'm just going to go to this website. I literally just typed in maze generator and just generate a maze. Make it. Let's take 20 by 20. That's good enough. Just going to download it and save it to you. Where did you save the thing? Yeah, so if you go onto the maze generator website, you should be able to get a PNG from that, and then this PNG can be interpreted by the Python scripts. Right, why are you scared? just making sure. Is it saved? Yeah. Cool. So we got this maze. It's really tiny. Where is the maze? Okay. Cool. So if we run this, let's run this code now. I'll show you what it does. I think it's set to, so it's first set to Dijkstra's, but if I go, Which? Oh, sorry. That should be under. No, that's fine. Path planning. Run this. You have Python. Do you?
Python 3.
Oh, so Python. Oh, I can see. Okay. So if we have a look, non-type as no. It's not open. Oh, that's fine. It's not reading it properly.
Maze.png.
It's not opening. I don't think in maze.png saved that. Okay. Work in your computer.
You go to folder work.
I think it's going to use.
Did I change it? No, I didn't change it. Oh, that's it. Yeah, why isn't it?
Oh, you need CD. It's not the same directory.
Okay, so is it? There we go. Cool, so we can see it's solving this maze in real time. Alright, so we just passed into PNG and we can see these branches here. It's a bit fast, I'm going to slow it down actually. Let's go change this here. Where is it? Oh, here. Let's go 1 second. Oh, maybe not 1 second, maybe like half a second. Quarter of a second. It's still really fast. Oh, I didn't say that. Oh no, I'm modifying the wrong one, sorry. I know it's not a thing. So we can see, just like we went through before, this is the Dijkstra's algorithm. So it's searching for the paths, and it's in this case it's sort of acting like a breadth first search, since each step only takes a distance of 1. Right? We can't travel diagonally in this. Right, so it's spreading out the search. I might have said it too slow. But we can see that the color in here represents the distance traveled. So anything that's the same color-ish will be equidistant from the start. So it's going to run through this algorithm slowly, very slowly. Oh, this is painful to watch. Come on. Yeah, have a go running this yourself. So again, it's on the GitHub. You need to make sure that you're in the same folder as it and download a PNG of this maze. I'll put it up. I think I also put it up on the GitHub. Nearly done. Cool. So yeah, now you can see that it's found the shortest path, right? And this is going to be the optimal path, right? Now, if we run this same thing again, right? Let's just keep a. Can we take a screenshot? Just so we can. Yep. Sorry, I haven't used a Windows computer in a while. So I'm just going to save a copy of this just so we know what the output was. And I'm going to run this same thing again, but with the A-star algorithm, right? So remember the A-star algorithm uses a heuristic for its priority queue, right? So instead of sorting by the one with the least cost, we sort with the one with the least cost plus heuristic, right? And in general, we want the heuristic to underestimate the cost in order for the path that it finds to be optimal. Right. Cool. So I'm going to run this again. Hopefully, I've done this right, and it'll give us the same output. The same optimal path rather. So we run this again. No, let's not make it that slow. Yeah, let's make it 50, 20. You can still see that's a lot faster.
And I got my first one.
Cool. And then comparing that against snipping tool,
I reckon, yeah, give us like this.
we can see it gives us the same path, right? Except we notice that for the Dijkstra's algorithm, it's explored this sort of region here, right? Whereas when A star, it only explored a bit of that, right? Because it was trying to optimize to travel further away from the origin.
What heuristic did you use?
For this, yeah, that's a good question. So for this heuristic, I used Euclidean distance, right? But there are a lot of other heuristics you can use, such as the taxi cab metric, which is just taking the sum of what is it? The sum of the distance traveled. So if you travel from here to here, it'll be that plus that. But the main thing with a heuristic is that you don't want it to overestimate the total cost of your optimal path. That's what it makes sense? Yeah. Cool. A nice thing with this is that if you have something like Paint, you can just open it up. So let's do that now. It's in here. Do you have Paint?
Yes.
Yeah, let's open it in Paint. I'm just going to edit this. We zoom in, yeah. Yeah, there's some advanced image processing right here. So I'm just going to color this and just to, oh, that's not the right color. Let's go. I'm going to draw out a path for it. So this is an obvious path. So if it doesn't go here, we know there's something screwed up. So let's save this and run it again. Cool. So you can see now there's a few more paths to explore since we've basically opened up the maze. But if we've done this correctly, it's just, yeah. So you can see that's the optimal path. Cool, and then I'm just going to run this again with Dijkstra's, just so we can see what happens. Dijkstra. Oh my god, okay. 250, changes to 50. So we can see, yeah, it's exploring this a lot more than it needs to. But again, it'll give us the optimal path. Yeah, this is taking a lot longer. Very impatient. I'm not. I'm just kidding. Yep, and that was the same path we got to before, which is what we expect. Cool. What should we do now? What time is it? Got about 5 more minutes, so. Oh, that was the one before was A star. Yeah, I'll do it one more time. So, yeah, that was Dijkstra's, and A star, because we're using the different heuristic, it's a lot faster to solve, and it's still optimal, which you want to do if you want your algorithm to be as fast as possible. Nope. Let's go. So I forgot to mention, this is using a Python library called OpenCV. So yeah, this is what lets it plot everything as pixels like this. So if you're having trouble running it, make sure you install OpenCV. You can do that using pip, which is are you all familiar with what pip is? Hopefully. Okay, that's good. So you can install pip install OpenCV Python. It's also useful for other things like computer vision, but I'm just using it in this example, which I made. Cool. So yeah, you can see it's not exploring this top region here. Cool. Yeah. Ash, would you like to finish off, Ash?
Not really, no.
Not really.
Where is the slides?
Is it slides? I don't know.
Oh, it's just a wrap up there.
Yes, wrap up.
Okay, thanks everyone for coming.
Thank you.
That's the, so in summary, yeah. So in summary, we went through the DFS, BFS, Djikstra, UCS, and A-star algs. And yeah, I enjoyed the quote slides, that was pretty good. And I went through some graph theory. But I want to leave you on a final quote from a very well-known man that I know. For many of us, the road is a difficult one, but there is always a path for us to follow. Yes, you just want to say anything? Go on.
Awesome. Well, thanks everyone for coming tonight to the UQCS and UQMARS path planning workshop. Hope you guys all had lots of pizza. In terms of events over the next couple weeks, I know both Mars and CS are going to be very busy. So we've got a resume roasting and like how to hack your interview sort of thing happening next Tuesday at 5 p.m. I think Mars have a movie night that's happening at the very similar time.
We're doing it with FPS and Snack Tuesday.
Snack, yep. They're watching Ghost in the Shell. It's also really cool. And then following week for UQCS, we also have our end of sem drinks and our movie night as well in that week as well. So keep your eyes peeled for that. But yeah, thanks everyone for coming tonight. And yeah, we'll see you guys around.
Well.